So thank you for joining me today. My name is Tomer Teller, and I'm a security program manager in Azure Security. In the last 2 years, I've been working on a security service called Azure Security Center. Raise your hand if you heard about it, play with it. Oh, nice. So if you ever received a security alert, an email saying that you have been breached, outgoing DDoS attacks coming on your machine, someone is doing port scanning on your machine, that's coming from our service that we developed. So today we're going to talk a little bit about the inner working of how to productize that and how you can generate insights from your services and your custom application, how to generate the same algorithms. So having been working in the security industry for quite some time, I've noticed that productizing threat detection models in the cloud is different than doing that on-premise. Specifically, being the cloud provider, the owner of the infrastructure, gives us the opportunity to detect this kind of unique cloud attacks that we're going to see today differently, using insights that we generated from the infrastructure and from the underlying services that make up the cloud. Today, we're going to walk through a couple of interesting case studies and see how these unique insights help detect these kind of threats. These insights are generated from what we like to call the cloud effect. This is something that we're going to talk in details today, and you're going to see specific example how having a bird's eye view of the cloud gives us the opportunity to detect cloud attacks differently. But before we begin, I would like you to think about the following scenario. An attacker compromised a set of virtual machines in the cloud using a zero-day vulnerability or perhaps just a misconfiguration, perhaps bad security practice, and deploy malware on that machine. Once the malware is deployed, a couple of days later, it contacts a command and control that orchestrates an attack on victims online. This is a classic botnet malware communication that we keep hearing about in the news every day. It's not new, and it's definitely not unique to the cloud. However, what if an attacker decides to expand his foothold? In the cloud, he has a couple of opportunities. One of them is what we like to call compromising a region. An attacker might lateral move between the different data centers and compromising more and more resources across the subscription and across the tenant. Again, this is not very unique to the cloud. Every organization that has a multi-data center strategy is impacted by this kind of vulnerability. Finally, what will happen if an attacker will decide to weaponize the cloud for his own advantage? In this scenario, an attacker will modify a set of simple configuration changes and scale up and scale out his attack, harvesting the power of the cloud for his own advantage. This is something that is very unique to the cloud, scaling up and scaling out. And using that huge amount of computation power, you will be able to take down more targets. How would you detect such an attack if it happens inside your organization? What kind of signals would you collect from the underlying services and your underlying applications in order to detect that? How would you stop that? I hope that by the end of this presentation, you'll have enough insights to understand how to productize these such of signals on top of your own custom applications. But in order to start answering those questions, we need to understand that the mindset in the cloud is different, has shifted. So things have changed from the day on the on-premise, and these changes affect how attackers operate and compromise computers and services in the cloud. For example, as an attacker, when you're attacking an on-premise environment, a data center, you're likely facing servers. In the cloud, there's a different animal called services. Of course, that's a service under the hood, and of course, you can set up your own ISVMs in the cloud, which are just normal service, but that's not what the cloud is for, right? It's all about services, which means that the attacker needs to upgrade their arsenal, the tool arsenal, their skill sets in order to compromise them. We're going to see later a couple of examples how attackers are compromising services and what is the difference between that and compromising the server. Same goes to a domain. As an attacker, the first thing you want to do is control the domain, have what we call domain dominance. In a cloud environment, it is likely that entity would be a subscription. If you own a subscription, you can do a lot of damage. You can spin up new virtual machines. You can take them down. You can eavesdrop on user. You can modify the data. You can tamper with the data that users are consuming. A lot of damage. Same goes to the persona, right? So if an attacker wants to get a hold of a domain admin, in an on-premise environment in the cloud, he wants to get a hold of a subscription admin. Subscription admin has a lot of power. In terms of lateral movement, we all heard about pass-the-hash techniques, right? It's a simple technique that allows an attacker to run some tool on a machine. You probably heard about Windows credential editors or the famous Mimikatz utility. You run it on a machine, you extract some credentials, you extract some hashes, and you use it to lateral move inside the environment. In the cloud, there's a different set of authentication. There's token, there's certificates, there are connection strings. It requires different skill set and different tools in order to do this lateral movement. We will see that soon. Same goes to the IPs, the IP domain. If we're used to having on-premise everything behind a firewall, everything protected behind a perimeter, in the cloud we're back into public IPs, which means that old school attacks such as brute force is back in 2017. When was the last time you heard about a brute force attack? In the cloud we hear about them a lot. We will see examples soon. And finally, managing these resources. Of course, when you want to manage a resource on-premise, you're doing it using RDP, using SSH. In the cloud, you're going to use management APIs. Now look at the list on the right. That's a huge opportunity for the defenders to collect insight from the infrastructure and from the underlying services, because the attacker has to interact and increase its friction with the network. It's a huge opportunity for the defender side to detect threats. We will walk through and see how it works. Now, so attackers need to productize new tool sets in order to compromise the cloud environment. And this also affects their kill chain, the way that they're lateral moving inside the environment. If you're familiar with the Lockheed Martin kill chain, the concept is pretty simple. An attacker has to go through a set of stages to compromise an organization. As defenders, if we break one of the stages, we can slow down the attacker or offend them. In the cloud, that kill chain is a little bit different. For example, if an attacker wants to compromise an on-premise environment, he's going to leverage passive reconnaissance, human intelligence, open source intelligence, to find that weakest link inside the organization. That could be using LinkedIn and Facebook and Google, a lot of ways to build a report, a profile on someone who you want to attack and then deliver the attack. In the cloud, there is no such thing. There is no human that we're attacking. It's all about services and the services and servers, which means that we need to actively reconnaissance the environment. Again, huge opportunity for the defender side to generate IOCs, to generate more analytics to see that someone is doing that reconnaissance. What about the delivery phase? So many ways to deliver attacks on-premise. You can use a browser exploits. You can use an email attachment with a malicious document. You can use USBs, you can social engineer, you can do some phishing. So many techniques to target someone and so many personas in the organization you can target. In the cloud, there is no user interaction. Well, in server environment, there's no one to double-click your attachment or to visit your website. You need to directly attack those services. Again, more friction with the network. Exploitation, client side, in the server's environment, in data center, obviously we're moving to server-side vulnerabilities. Equifax attack last month, Apache Stroud vulnerabilities, these are the kind of vulnerabilities we're seeing in the clouds. Here's another interesting aspect of on-premise versus cloud, or more likely on-premise versus data center servers. On a client machine, on a PC like this, on a desktop, these machines tend to reboot quite often. So attackers, when they compromise these boxes, they usually drop a malware on the machine and they persist in it on disk, which means that when the system reboots, the malware loads itself again. In a cloud environment, specifically in the data center server environment, the uptime is much larger, which means that they have the luxury of running straight in memory, which means that the tool sets and the post-exploitation tools attackers are using usually are memory-based. Again, different type of defender techniques that we need to apply in order to detect them. Same goes to internal reconnaissance. When an attacker wants to find out where he needs to go next, there's the fog of war. When someone is compromising an organization, there's a big fog of war. We don't know where we want to go. So the first thing you want to do is understand the network. Usually on-premise, an attacker will bring an arsenal of post-exploitation tool, will run some tests, and understand and start mapping where he wants to go next. In a cloud environment, specifically in a server environment, it's very nice that you already have a predefined, a pre-built admin and DevOps utilities that he can use. And usually these tools are already whitelisted if there's an app locker or credential guard, uplooker policy running on that machine. So it's pretty interesting to see that attackers are using whitelisted, allowed utilities to execute an attack inside an environment. And finally, lateral movement. So if you're used to on-premise running Mimikatz and doing what we call machine pivot, jumping, hopping between machines, no longer in the cloud we're doing resource pivot. A resource could be an IaaS, could be a PaaS, could be a storage, could be a key vault, could be a cloud service, could be a custom, could be a function, could be everything. How would you detect that? So not only the cloud mindset has shifted, but also the way that the attacker modus operandi, the way that they operate in the cloud. And this raises even more questions. Where should we instrument our monitors? What kind of insights and signals we want to extract and generate from the infrastructure, from the services? Think about it. If you ever read a security best practice guide, they usually tell you, OK, you need to harden the machine. Here's a list of hardening. And we want you to collect process creation events and turn on command line auditing and PowerShell activities and DNS activities and login events and fail login events. Send it all to your SIEM. And on top of that, build a set of security analytics. I bet some of you, all of you have already seen these papers. They're all over the internet. That's nice when we're talking about IaaS machine, Windows or Linux machine. But what kind of insights or signals you want to collect from a storage account? Or what kind of signals you want to collect from a function that execute immediately and exit? How would you detect threats in these kind of resources on entities? This is the kind of mindset I want to share with you today. So if you're building a custom application that is built upon these kind of services, you'll be able to think like a defender. So in order to answer those, let's look at a couple of interesting case studies that illustrate how attackers operate in the cloud. These are unique cloud attacks that you won't see on-premise. And I hope that it will open your mind to the kinds of signals and insights we need to generate and collect from the infrastructure and from the services in order to detect them. The first one I like to call in public secrets. It happens, and it's an attack that happens every day. Many cloud applications, as you know, are open source or using open source application. And in this scenario, a developer commits some code into a public repository. It could be a GitHub, GitLab, Pastebin, perhaps a storage account. Without even noticing, the developer also commits the application secrets. Secret, as we saw earlier, it could be a token, could be a connection string, could be a certificate. Without even noticing, he's pushing those secrets to a public repository, unknowing that these secrets are password equivalent. All the attacker needs to do, and that's exactly what they're doing, is productize a utility that will scan all these public repository and find those secrets. Attackers are doing it every day. We just heard a couple of weeks ago how a storage account in an S3 bucket was not vulnerable, was only word readable by mistake and contained confidential information. That was a security best practice. All the developer had to do was remove that read permission from that account. Attackers are looking for this kind of storage account, looking for this kind of public repository to find those secrets, and once they find them, they compromise the resource, and they can run a lot of havoc. If it's IaaS machine, they will run a Bitcoin miner, they will do a DDoS attack. If it's a storage account, they will steal the data. If it's a key vault, they will steal the keys. Everything is a target, and everything has its own set of security rules. Is anyone familiar here with the attack matrix? See some hands? That's a very nice specification, a list of matrix of security incidents that happen, and a set of signals you want to collect in order to detect them. In the clouds, it's a little bit different. Every service has its own matrix. And if you're deploying an application that's using those services, you should be aware of that. The next attack is what we like to call resource ransom. If you thought ransom is only about virtual machine, Linux and Windows machine, well, forget it. Attackers are looking to expand and get more money. And where's that money? PaaS services as well. In this scenario, an attacker managed to access a storage account, for example, or a vault containing passwords or keys or tokens. Once the attacker got access to that, he will encrypt the data, or he will steal the keys, or in some cases we've seen encrypt the keys that decrypt the data. So all the attackers need to do now is walk back to the developer, tell him, hey, you owe me some money. The developer has service disruption. He's not allowed to use, he cannot use this service. That's pretty bad, and we see that. It's not very trendy so far, but this is a possible scenario that once an attacker got access to a resource, they can do. Fortunately, in the cloud, some of the services has rollback functionalities and backup functionalities, so sometimes it's easier to recover more than a virtual machine. But again, that's a feasible scenario. And the last one, if it's not enough, here's a scenario that was revealed by our red team activity earlier this year, was published in a security conference called Infiltrate. In this scenario, an attacker managed to compromise a subscription by stealing someone's identities. As you know, there's a lot of leaked databases out there, people forgetting to put two-factor authentication, reusing their password, so many ways to steal someone's identity. And once they manage to access this subscription, as a subscription, what you can do, you can deploy new services. A new service that is deployed inside a service, inside a subscription, automatically inherits that subscription secrets in order for it to operate inside that subscription. So in this scenario, an attacker compromises subscription, spins up a service. That service inherits the secrets. All the attacker needs to do is connect to that service, dump the password, dump the certificates of that deployment, look at the permission model and see, hey, where can I go next? You see that he can go to this kind of subscription. He will use that, hop into that subscription, deploy a new service, dump the credential, dump the certificate, look at the permission, and on and on and on. And that's the equivalent for pass the hash in the IaaS world, in the cloud world. And once he found his target, he finds the data, he do whatever he wants, he can exfiltrate it outside, game over. So we've just seen a couple of unique cloud attacks, things that don't happen on-premise, things that we as security researchers and professionals never seen before. And the cloud provides us a huge opportunity to detect these kind of activities. And just like any modern enterprise, we at Microsoft also adopted the assume breach mindset, which is important. The idea is pretty simple. Try to defend the castle, try to prevent, recommend prevention mechanism, do whatever you can, but also adopt the mindset that you might be breached and someone will manage to get inside your organization. So we're shifting our thought from being perimeter focused about doing all the threat modeling and external testing all the time to what we call assume breach mindset. We're productizing threat detection models, which means security analytics. You probably heard a lot in the news about security analytics. It's a big buzz going on. It's not a buzz. Continuous monitoring, making sure that you see that you collect the right data and you test it to see whether you find some interesting threat scenarios. You need to have an incident response and recovery plan. In case something happened, you need to automatically execute it so you can limit the attacker to expand inside the network. And finally, you want to test it all the time, continuous testing by doing red team activities. Now, at Microsoft, we adopted the detection engineering process to productize this kind of security analytics. Now, I like to think of this process as a well-defined process. And it first works by learning about an attack, right? You hear about an attack in the news. It could be in a newspaper. It could be in a conference. It could be a research. It could be a bug bounty. Someone tells you about, hey, there is a new attack vector, just like the one I just showed you with the cloud pivoting attack. Once you learn about it, you simulate it in a highly instrumented closed environment. You want to run it as much as you can and learn about this attack and what kind of signals it generates inside your infrastructure. Remember, the cloud is made out of services. Each service may affect another service. If you execute a file on a VM, it affected the storage, that affected the billing, that affected the CPU performance counters. Each one of them are different services. Think about it. Each one of them generates a different log. You don't need to be inside the VM to understand what happened inside the VM. Keep that in mind. So we run the attack. We look at the threat scenario, at the entire narrative of that attack, and try to pinpoint and cherry pick the right signals to detect that. Once we extracted the DNA of the attack, the right amount of data that will detect this kind of attack with the least amount of noise, we're moving on to productization, which essentially is, let's build a security model that will detect it. It could be a signature, it could be a behavioral model, or it could be a full-blown machine learning algorithm or anomaly supervised or unsupervised. We'll get to that soon. Finally, once we release that model out there, we fine-tune it. We make sure that we continuously train that model or modify it. So we reduce the number of noise, reduce the number of false positives. And the beautiful thing about it, and John Lambert, a well-known security persona in Microsoft, once coined the term Fibonacci hunting, which I really like. And the idea is pretty simple. You productize this, you're using this process to productize an alert, and it goes live to production. After a couple of days, there's a hit at one of your customer sites. That customer start to hunt that alert to understand whether it's a true positive or a false positive, the scope, the root cause analysis. Once he found that, he generates a report and he generates new artifacts that lead him for 2 new more compromises. These 2 new compromises generate 2 new alerts. These 2 new alerts generate more hunts, and it feeds like a Fibonacci series. That's why we really like this. I really like this term. Now, this process is useless without what I like to call the detection stakeholders. And at Microsoft, we identified 3 detection stakeholders. The first of all is the security analyst. That's the security researcher that knows and learns about the trends, that simulate the attacks inside closed environment, making sure that he can catch them, or making sure that he can execute them inside the environment. He pinpoints the data sources that are needed to collect. Sometimes there are blind spots. Remember, you cannot monitor everything all the time. There's a lot of constraint. It could be volume, it could be costs, it could be permissions. So he pinpoints the location that need to be collected, and he writes a report about that. The security analysts also work hand in hand with the applied researcher / data scientist. The data scientist, applied researcher job is to extract features from these data sources in order to train models with incomplete data. And I'm saying incomplete data because most of the algorithms, and if you experience some security alerts in Azure Security Centers, most of the algorithms that we productize, we run on incomplete data. And we'll soon see a couple of real examples of how we productize them, how we generated high fidelity, high severity alerts with incomplete data, without having access to everything on the system or everything on the network. And finally, he works hand in hand with the security analyst to fine-tune this security alert. Finally, we have the security program manager. The security program manager job is to learn about this threat scenario from the security analyst or from the news or from the customers and define those and bridge between the stakeholders. Of course, doing the entire prioritization. He needs to work with the different services team, especially in Azure, in Microsoft. My job sometimes is to go and hunt for a specific signal. I know that if I had access to this specific signal that the customer collects, I will be able to generate a high fidelity alert and move from a 60% precision to 90% precision. This is huge. But we also need to mix in customer constraint, which is not that simple. In the cloud, obviously, there's some constraints. It could be PII processing. We're not allowed to process some confidential data. It could be geolocation restriction. Think about an attack on a data center in Europe, an attack that just lateral move to a data center in US. GDPR rules doesn't allow some things to move between data centers between those regions. How do you exchange any information to detect this kind of attack? There's also the volume. The data that we generate, there's a lot of volumetric signals that if we collect will cost the customer a lot of money. So we need to keep in mind all these customer constraints. Now when you take the stakeholders and you glue it with the engineering process, we get what we like to call internally the detection factory. This is a well-defined process that we run in Microsoft. Every time we hear about a new security alert, the program manager, the security analyst, the data scientist work hand in hand in order to productize an alert. Let's see an example of how it works. So let's go back to the attack we talked earlier, the resource ransom. In that case, someone compromised the resource and tried to demand some ransom because he encrypted some data. How could we have detected that attack? So first of all, we learned about this attack from a customer. The customer said, I want to detect ransomware on my machine. The first thing you would do in order to detect ransomware is obviously run on that machine. Use API hooking technology to see whether there's a ransomware activity running on that machine. Using API hook is pretty much the easiest way to do that. Almost every security company is doing that. However, we released that analytic, and a couple of days later, a customer came with another constraint. I cannot hook my specific VM. Why? Performance degradation, or there's a real-time application running there. I cannot destabilize the system. I don't know. Sometimes there's these kind of constraints that we're not allowed to do. So we had to think and say, OK, how can we detect ransomware without API hooking? We had some brainstorming, and we came up to the thought, let's detect it using ETW traces. As you know, the kernel components in Windows, most of the components in Windows has some generate ETW traces that allows you to trace the application of what's going on. You can register on some of these ETW providers, and on top of them, understand and profile the system. So we pinpoint the right ETW providers that we want, and we productize that analytic. A couple of days later, a different customer came and said, that's great, I need to detect ransomware on my machine, but I'm not allowed to install any agent on the machine at all, because I have some PCI rules, I have some restriction in that specific area. Now that's challenging. How would you detect ransomware on a machine without actually being on the machine? And this is where I think this engineering process works really well. We want to detect ransomware using side channel signal. So how does it work? If we dive into the process, we start by learning about this requirement. The security program manager learned about this requirement. He involved the security analyst. The security analyst, in that case, executed hundreds of ransomware families and variants inside a virtual environment, inside the cloud, and watched how the ransomware affected the different services in the cloud. Then he worked hand in hand with the applied researcher to cherry pick the right signals from the right location to detect that activity. Apparently, when you run a set of ransomware, some of them will try to lateral move. We will see some signals and artifacts or side channel signals inside the AD. Sometimes, if the ransomware is going to do a lot of scanning on the machine, it will consume a lot of CPU power. The billing will rise a little bit, but it will have some changes. Perhaps the malware is going to encrypt some of the files and commit them to disk, which means that the storage just had a unification of file being changed. Perhaps the ransomware contact the command and control to receive the public keys in order to encrypt them, so you contact the network. Think about it. All these different components generate insights. We cherry pick the right one in order to detect ransomware activity. So the analyst and the security and the data scientists work together to train a classifier to essentially distinguish ransomware, not ransomware. So what the attacker, these two guys are doing essentially is they're running a ransomware on one machine, they're looking at the other surrounding services and see how it affects them. And for that, they cherry pick the features to train their machine learning algorithm. And the result is a security analytic which has a 95% precision without being on the machine, which is pretty awesome. Now, all this process that we just talked about, we need to owe it to the rise of AI. You need to understand when you're dealing with cloud scale, everything you do starts and ends with big data. And this is a great opportunity to research machine learning algorithm for security. I think that 10 years ago, if you tell me, let's run this random forest algorithm, I would say I don't have enough data, or I don't have enough signals, or enough labels. When you're running in that scale, you have a lot of data, which allows you to do a lot of interesting things. Now, in the cloud, I identified two types of signals. The first one is what I like to call explicit signals. These are signals that are being generated from operations that you executed on a machine. For example, you ran a web server, an IIS log will be generated. You executed a process creation event will be generated. You deployed the service on your subscription, that subscription will generate some trace that you'll be able to collect. These are all generated by an operation you did. However, there's another set of signals that we identified called, which we like to call implicit signals. These are signals that are generated indirectly from operation you did, like the things I described. For example, when you did a memory operation, Hypervisor generates a set of traps. When you hug the process, billing did a little bit of, increased it a little bit. When you stored something in your VHD, the storage account generates a couple of logs. Think about it. Everything you do when you're running on a managed service affects different services. It's a huge opportunity to collect signals. However, as you know, when you're productizing threat detection products, it always comes with a price of false positive. And you know, false positive, we can't avoid false positive. And those who will tell you that what they're doing every day is to avoid false positive is lying. The idea in security is to live with false positive, but generate tools that will help you avoid them, which means reduce them using automated confidence scoring or reprioritizing them. You don't want to. There's sometimes, think about it, when you're productizing a security analytics, sometimes it's you want to productize an alert that you know will generate a lot of false positive. For example, if someone connects to your machine, let's say your service is in the United States, you're generating a new analytic that says every time someone is connected from outside of the US, generate an alert. Obviously, this is a geo anomaly. We're expecting to have false positive by design, and it's fine. The question is, how can we solve it? Now, as you know, anomaly detection is the identification of anomalies patterned in series of data. And there's a big problem with anomaly detection. Some of them are good, some of them are bad, but most of them are hard to attribute. Look at the graph below. It plots the SMB port scanning activity in Azure from January until May. We'll get back to that very soon in an example in a couple of slides. But just by looking in a graph, think about it. If you're now a security manager, you're sitting in front of a big screen, someone just plotted the big port scanning activity, ask you, hey, can you explain that peak? I guarantee that most of the people will not be able to understand what caused that peak. All I know is there's a peak. In order to solve that, we need to enrich and label these signals to uncover the real threat scenarios. I want to know what is behind that peak. And in order to do that, anomaly detection is not enough. And Microsoft has a huge advantage in that area because Microsoft generates labels and receives labels from many services. For example, we have a lot of domain experts in different service teams. The job of these guys is to mark something, whether it's good or bad. So if we have a team that dedicates itself to malware, they will write malicious or benign. If there's a team that wants to understand spam, they write spam versus no spam. If there's a phishing URL, phishing, not phishing. And they write it down inside a huge database that we at Microsoft have and allow us to label and use it when we train our machine learning algorithms. These labels can come from security products such as Azure Security Center, Windows Defender ATP, Office 365. They can come from red team exercises that we're doing. We have a yearly red team exercise at Microsoft, all the red team versus all the blue team. This is a great opportunity for us to learn how the red team, the new activities they're doing, and each time we detect their attack, we write down, we label that, detected. Each time we miss, we try to hunt for the signal that will allow us to detect it the next time. We have internal team, MSRC, that generate these kind of labels. We get it from security researchers. We get it from customer feedback and sometimes customer complaints. If a virtual machine in Azure will start to DDoS someone else, it's our job to detect it and take it down. But sometimes someone will complain and say, hey, that machine is DDoSing us. We'll check it. If we'll verify, we just added another item to our list of labels. So simply put, when these labels gives us the opportunity to move from and train our models and turn it from an unsupervised problem to a supervised problem. And this capability allows us to generate high severity and high fidelity signals and filter out the noise. Let's look at a couple of unique algorithms that we productize in Azure Security Center that will show you how we combine signals, labels, and the cloud effect that I talked about earlier, the ability to have a bird's eye view of the cloud to detect attacks in high precision. The first one is around SMTP anomalies. Now, when we monitor Azure networks, the first thing we wanted to do is to understand whether some of our customers are compromised. How do you know if a customer is compromised? His machine is trying to doing outgoing DDoS or outgoing spam or outgoing port scanning. So how do you productize such a signal? Well, the first thing you do is you collect network signals. We do that using IPFix. We have access to the IPFix, to the cloud network, and we are able to see exactly what's going on. However, if we just look at port 25 at SMTP traffic, every day we will see a lot of anomalies, a lot of spikes that we won't be able to explain. And I cannot just go to every customer and say, hey, on Saturday between 2 and 4, can you explain that peak? No one will be able to say, and probably they won't even know that that happened. So it's our job to find it and productize a model that will generate. And obviously, we want to reduce the false positive. We don't want to, every time there's a peak, to tell them, hey, you have an SMTP anomaly. We want to uncover the true hidden scenario behind it. We want to know whether it's a spam campaign. And it's a huge difference between an anomaly and a spam campaign. And how do you do that? Now, in order to do that, we partner with the Office 365 team. The Office 365 team, apparently every email that leaves Azure goes through Office 365. Office 365 has an spam algorithm that marks spam, not spam, on each emails that leave. What we can do is pretty simple. We can look at the IPFix signal, and we can spot an anomaly, and then we can ask Office 365, hey, is that session that we just saw, is it spam or no spam? And by that, understanding and finding the right signals we need to collect from the network feed in order to detect it, which means that we're using the Office 365 signals to understand which features from the network, the IP, the TCP flags, the length of the connection, the size of the connection, in order to productize a high-fidelity model. And all that without even looking at the email. We don't need to look at the email contact. All we need to do is look at the network and see what Office 365 sees. And the result is a high-severity alert, high-fidelity alert in Azure Security Center, in this case, that differentiate between an SMTP anomaly and a spam campaign, telling the customer, hey, your machine is compromised and participating in a spam, which means that it's compromised by a malware and doing something bad. Another interesting example is around network anomalies. Now, as I mentioned earlier, once an IaaS machine, a virtual machine, is getting compromised in Azure, you know what the first thing attackers are doing? They usually know that they're not going to stay there for the long term. So they're harvesting the power of the cloud for their own advantage, which means that we're seeing a lot of Bitcoin activity. We're seeing a lot of outgoing brute force, outgoing port scanning, and the most popular is obviously outgoing DDoS. While the machine is up, let's use it to attack others. So in order to detect that, in order to detect this kind of SMTP, detect these network peaks, we again look at the network traffic, at the IPFix traffic. And every time we're seeing, and we're building a profile on each one of our customers, and whenever we see that machine is suddenly contacting a lot of ports with a burst, with a huge volume, we know that's a DDoS. It's pretty easy. Actually, it's really easy to detect volumetric DDoS. However, there's a big problem. There's another set of DDoS, which we like to call low and slow DDoS, which is a DDoS that likes to mask itself under legitimate traffic. So when you profile the machine, you see that it's a little bit over the threshold. However, it's not that high. It's not DDoS, but it's more than just legitimate. So it's maybe DDoS. But I cannot alert you every time I found a maybe DDoS in your environment, because I'm going to flood you with a lot of false positive. So in order to solve that, again, we leverage the fact of what we call the cloud effect, our ability to look at the cloud in a bird's eye view. And what we did in this specific research that was productized in Azure Security Center was we looked at virtual machines that we suspected as maybe DDoS, that are a little bit above the normal threshold, but below the volumetric threshold. And we clustered them together to see whether they share the same characteristics, whether they're contacting the same IPs, whether they're sharing the same, contacting the same area, maybe they're doing a lot of volume, maybe they're sharing some characteristic together. And using that specific model, and we're exploiting the fact that in order to do DDoS, you usually need more than one. And more than one machine participate usually in the DDoS. So we always find this kind of clustering in Azure, and we group them together and telling those machines, hey, even though you're not a sure thing DDoS, we're we, in high confidence, believe you're DDoS because you're sharing similar behavior with this machine and this machine that are participating in DDoS. And the beautiful thing about it, we can retroactively verify that our model was correct. A couple of hours later, after a machine was compromised with a DDoS, their IP address will appear in the TI feed, in the threat intel feed. It may come with a complaint. So retroactively, we know whether we were correct or not, and we fix our model. So it's feeding the model with new labels all the time, and we know whether we were correct or not, which is awesome. Now, this is all great. We talked a lot about threat detection, but the question is, can we use this kind of threat modeling to also do threat prediction? We all heard about the WannaCry attacks. Well, you probably, when you saw this graph, I said it was port scanning activity on the SMB port. I guess some of you, the light bulb said this is probably WannaCry. So when we all heard about WannaCry, we all heard about WannaCry that took place in May. And it was only a matter of time until the attacker will leverage the Eternal Blue vulnerability that was leaked from the NSA. But the problem is no one really knew what they are going to do with it. It was like over 2 weeks that the 0-day was out there. Microsoft already released the patch, but as you know, people sometimes take their time until they update the machine. Why does no one actually using that vulnerability yet? Could we have predicted WannaCry in advance? Or more importantly, can we learn retroactively from the WannaCry attack to predict the next attack, next usage of a network exploit? Now, what you see on the graph here is the SMB port scanning activity as detected by Azure Security Center. Every time we see a port scanning, someone is port scanning, spraying some of our customers, we alert them, hey, someone is doing some reconnaissance on your organization. Our ability as the cloud effect here is our ability to plot this kind of graph, to see it, look at all our customers, and show you all the port scanning that happened to all of our customers. Now, when you see this kind of graph, it's still not explainable. If you just look at it and see, hey, OK, there's a WannaCry attack happened on May, and I see a peak, perhaps it makes sense. But for an algorithm, it's not enough. We need to enrich it with more label. And in this case, let's look at the graph. There are 3 interesting anomalies that happen in the graph. The first one happened here, the second one happened there, and the third one is the large peak that we see over here. If we take those anomalies that happen on the graph, those little peaks, and we enrich it with items, news items that happens on the same day, especially CVEs and Microsoft Bulletin, we'll suddenly uncover the true narrative behind this attack, right? Suddenly, this peak is explainable. And the way I would explain it is Microsoft released a patch. A couple of days later, a couple of researchers reverse engineered that patch to find a vulnerability and created some tool. That's the small peak over there. They were trying to exploit that vulnerability or try to scan for this vulnerability. A week later, someone productized this module as a Metasploit module, which means that it's widely publicly available for every kid scripty to run and test. And 2 weeks later, someone did a huge scan, and following a week later, WannaCry appeared. Suddenly, this peak makes sense. And using the cloud effect, it's our ability to actually predict and use this kind of information to predict the next large-scale network attacks. This is a great opportunity to learn from that. So if you think everything I talked to you about is voodoo, that it's not, most of these algorithms, most of the engineering process, the threshold that we talked, the data insights that we talked about today, the shareholders that we talked about today is all part of Azure Security Center, threat detection pillar. Now, some of these analytics that we productize, we execute in the system, we trace them, we cherry pick the right signals to detect them, we work with customers to fine tune them, and we did the entire process. So if we summarize what we've seen today, the cloud attack surface came with the price of a new attack types. We've seen unique cloud attacks that affected the cloud. In order to detect those, we came up with a new detection engineering paradigm, the detection engineering process and the stakeholders. This process allows us to fuel, using the Fibonacci hunting concept, allows us to fuel this process, this factory, with more and more analytics. Every time we hear about something, we add it to what we like to call the detection cookbook, and we keep adding more and more. AI and security works when you have a well-defined security scenario and we have big data with signals, and you enrich it with labels, you'll be able to develop and productize well-defined security models with high precision. And finally, some of these things are inside Azure Security Center. An Azure Security Center, and this is the process that we're running in Microsoft. So I hope you got some of the idea today about some of the insights that you need to generate. If you're developing your own application tomorrow and you're using some of these services, try to model and think, what kind of attacks are my application is vulnerable to? What kind of signals can I collect from the infrastructure? Where should I send them? What kind of insights I want to extract from them to detect these scenarios? Think about the detection process. Think about the data and stakeholders in your organization that can help you achieve to productize these kernel models. And these will give you the visibility you need in order to secure your application, your custom application, and eventually keep attackers at bay. Thank you very much. Any questions?
What's next? When's the next virus coming? You guys probably
Well, we're always looking. That's the beautiful thing about it. I mean, this factory is always fueling itself with more analytics. We hunt. We have data hunters. That's their job. They're looking at these security attacks. They're working with the customer to hunt. Suddenly they see, oh, there's a new technique. And they're productizing, adding it to the detection cookbook, and it fuels more and more security analytics. Yeah? Mm-hmm. Yeah. So whenever we see this kind of anomalies, the first thing we try to do is look for daily items that happen and try to enrich that signal so we can really uncover what happened. Because just by looking at that graph, I'm clueless. I won't know what I can perhaps think what it is, but in order for the algorithm to know, we have to enrich it with more context. Yep.
So what if your application or business is spammy or security scanning, or what does Azure not want the business, or is there exclusions? Is there ruling? Is there what?
So specifically, if you're running an application and you're running specifically Azure Security Center, we're monitoring the network. So it's pretty much application agnostic. If we see something bad going on, we don't know whether it happened from an application, from your OS, or from a resource, other resource. We monitor if it happens on the SMTP port, and we see that it's spam, for example, we'll notify it's spam, regardless of the application. So if you have your own third-party email server or email campaign, we'll be able to spot these kind of anomalies.
Yeah, my question more or less is it just alerting, or is there prevention happening, active prevention happening?
Yeah, okay. So in the cloud, you actually have I think at least that you have the luxury of doing threat detection and not threat prevention. Because of the way that the cloud services works, because there's revisions and backups and rollbacks capability to almost everything as a service, then you have the luxury of detecting it in near real time and then reacting to it using automation and orchestration. We literally introduced in Ignite now a new workflow that allows you to build your own custom workflow, which means if I see this kind of attack, do this and that. Post in Team, post in Slack, and react to that the way that you want.